Now, if I'm trying to grow layer by layer, I better know the details of what the reality is that tells me how it really grows as opposed to how I might think it grows. There are a number of ways of growing things. The molecular beam epitaxy is one which is used in the semiconductor industry, which involves layer of one material substituted for, and then a second material, and then back to the first and a second, so that I have a variety of different kinds of layers all built up in a very periodic array. That's molecular beam epitaxy. The image shows several different sources. So here's a target. Here is one source providing aluminum, for example. Here is another source providing gallium. Here is another source for arsenic and another source for phosphorus. And if I want to make complicated combinations, I shut off the source that I'm not using. So up here, I'm accumulating the materials that come from these two or these two or these two. So I have a wonderful way of developing blue lasers or green lasers or other structures. Both of those kinds of processes, physical vapor processes, give me growth when I can see the target. That's line of sight. But if I want to cover something that's more complicated, I have to change the chemistry. I can't use that particular process because line of sight doesn't coat things uniformly, but I want to. And a process that's been developed is chemical vapor deposition, and that's a particularly nice process because it takes advantage of the tendency of the vapor to stick to the substrate being very, very low. And that means that I can have a gas over a surface that's complex in morphology with a very small chance of it sticking. And that means that I don't have, say, an occlusion of the top of a crack. The image that's shown shows a deep trench. Now, a deep trench can be filled if the probability of a reaction occurring is very small. That means it's going to be equally likely up here on the flat part and down here on the side. So I will grow uniformly. Other processes would very quickly gum up the top and you'd never get to the bottom. The example that I show is a hafnium compound in the gas phase being delivered to the surface where a reaction occurs, and the hafnium stays behind as a hafnium boron compound, and the other gases get transported away. So that's chemical vapor deposition. Another way of growing materials would be a more energetic process. That is, instead of having a hot source where I'm evaporating, let's think about a target where I am driving atoms at it and sputtering atoms, that is, kicking them off from the target, and then they go and they stick on what I'm growing. That gives me an enormous amount of control over the processes because I have the kinetic energy of the incoming particle and I have the ionization state of the particles that are rejected. And this is a very popular technique for making hard coatings, for making materials where you want to control the structure and the engineering of it. Another process for growth would be analogous to what we have in, say, a smokestack. And that is where you have a small particle and it diffuses and it comes in contact with another one and it sticks, and it diffuses and it comes in contact with another one and they stick. And with distance from the source in this gas, I have larger and larger particles that form. And the picture that's shown shows that these are small, get to a particular size, and at any point I can pull off that size. If I let them get too big, well, then they're no longer useful because they've started to agglomerate, but I can control the size of the particle by where it is in the stack. And I can control the size by the density of the gas and the kind of gas. So this is a very useful technique called gas phase condensation. Another technique which is important, particularly in carbon nanotubes, for example, would be to take a very simple system. Let's have an electrode and another electrode, and my arms go connected to a battery so that as my fingers come lower and lower, there's a lightning strike, there's a discharge. And that process means that I'm evaporating the atoms from one of the electrodes, and there can be some interesting chemistry that results. If you have both of these as carbon, you can produce yourself a carbon nanotube. And that was done by Rick Smalley and Don Bethune and others about a decade ago. And Tom Ebeson, in the lower portion of this image, shows carbon nanotubes that have been developed by this process. And this image shows that there are two different kinds. One is where the electrode is pure, and the other one where it is doped with a catalyst. And depending upon the chemistry of the problem and the details, you could either get single-walled or multi-walled carbon nanotubes. Yet another way of growing things builds on good basic material science. That is, if I have a compound and I mix it with another, the melting temperature is going to drop. So in this example, we could have germanium and being flowed over a collection of gold where the gold is hot, and the germanium hits the gold, dissolves in it, supersaturates it, and as this image shows, the melting temperature drops. But if I keep feeding germanium into it, at some point I reach the point where I'm supersaturated and the germanium must come out if I'm going to add more in. And that gives you an interesting way of growing, as the image shows, a wire underneath this cluster. So here's my cluster sitting on a surface. It's accumulating germanium, and eventually it starts to spit germanium out in the crystal structure on top of the support, and then it rises as the process occurs. So it's growing a nanotube, in this case germanium, but it works for many other things as well. The TEM images that I show here follow the process. The first one shows just the particle, the second one shows the particle getting a little fatter as it absorbs material, the third one even fatter, and then the fourth one where it's starting to pull off. And then the fifth and sixth show the wire developing. Wonderful technique for making new and novel structures of materials. Everything I've talked about so far has been a solid state process. You can also do chemistry. So our colleagues in the chemistry side look at colloidal structures. And there they have a molecular beaker, which they coin after our molecular beaker epitaxy. The idea is simple. The process isn't necessarily. I inject one material that's carrying the atoms of what I want, and another, and in this hot soup, the two things that are injected dissociate. The atoms that I want are now free to swim around and find each other in an appropriate medium, and they can grow. And when they grow to a particular size, I want to try to control their subsequent growth, and that I can control by the soup that they're in. So it's a nice process, and here's what the idea is, the physics of the process. I inject, I go way supersaturation, and that means uniformly in the whole bath, I start to nucleate small particles. That means that the concentration drops rapidly, and when I get to a particular point, I want to make sure that those small particles don't grow anymore, so that when I'm all done, I have a uniform collection. In the image that I show, they continue to grow. The indication over there on the right, if I were to add something to the system, then that would prevent their growth. And here is an example of a capping agent. A capping agent is just exactly what it sounds like. It's something that protects, it provides a cap so that my two particles don't come together. They stay apart. And that means that when I remove them from the bath, I'm able to make a particular structure. So far we've talked about ways of growing things. Now let me spend a little bit of time talking about characterization. One way to characterize materials is with a transmission electron microscope. And I strongly believe that any materials laboratory needs such a device because you're able to see things in real space, as the image on the upper right-hand portion shows. Real space image. I can do diffraction, as the inset shows, or I can get really small focused beam and focus on the atomic structure of the particle. So it's a wonderfully diverse technique, and everyone should have one. Something which is perhaps not quite so common would be a scanning tunneling microscope. And a scanning tunneling microscope is what I've depicted here. There are several parts of this image, and it's a little bit complicated, so let me talk you through it. The cartoon on the left shows a sharp object over an array, a surface. So I can scan along the direction of my fingers or across my fingers. And what I want to be able to do is see when I come up on the knuckles. So that means I need something which has extreme sensitivity in the vertical direction and control in the X and Y direction. And that's what this shows. Connected to a servo loop so that I can control the current flowing. So what the idea is that I'm passing current from the tip to the sample, or the other way around, and measuring the current and holding the current fixed in general. The real system is shown on the upper right, and that's a picture of one of the instruments in our laboratory showing that, that this microscope is just a small portion of a bigger system, and that if I get even closer, then I have the portion on the bottom right, which shows the active parts of the microscope. And I'm not sure if you can see it, but there is something that's horizontal, which has the capability of moving X and Y, and also advancing in the Z direction, where I'm making Z the direction of my finger, and a sample that's sitting here at the end so that I can approach and then scan. Now we think of a tip as being sharp, and the picture there shows a sharp tip, but it's sharp on two different length scales. One is when you've got a fairly low resolution, and that looks sharp, but when you get up really close to the size of the nanometer, it's more curved. That's the reality of what a tip looks like. Here's a cartoon of a tip, and a cartoon showing what STM does. There is a tip where there is one atom on the apex, and all of the charge flows through that atom. And because of the equation that I've written there, the current depends exponentially on the distance between the tip and the sample. If the current were to emanate from the second atom, it would be down by, if it's 2 angstroms away, by a factor of 10 from the one at the tip. So the one at the tip is controlling all the current flow. And the moving picture then shows you that as you move across the surface, you want the current to be fixed, which means you rise up and down, and since that's easily measured, you're getting a topograph of the surface. You can see steps like that depicted. Scanning tunneling microscope, Binning and Rohr's development that immediately led to a Nobel Prize. As an example, let me show you a silicon surface. Silicon is one of our favorite materials in microelectronics. It's been studied for decades. It's very well understood. With STM, you can make new advances in understanding what the processes are. The image shows you a surface that's been miscut. It's like this table. This table is flat over here, but then there's a step, and then another terrace, and then another step. That's exactly what you see. On the top terrace, the atom rows are running one way. On the next one, they're running the other way. And so you can see rows going one way and then the other. With STM, we can zoom in on that. We can see what the atoms are doing, whether they're dynamic. If you look carefully along the row in that lower portion, you'll see that there's something that's bright, and the bright goes up and down and up and down. Well, that's easily understood now, of course, by saying that if I were a silicon atom, I would have 2 back bonds and 2 dangling bonds. And if you create the clean surface, I want to get rid of these dangling bonds. I want to move a little bit and form a bond with my partner who looks just like me, like that. Now I have a dangling bond, only 1. That's what these lozenge-like things look like in the current image. The fact is that there's this very small barrier that keeps me from moving up and down and my partner from moving up and down, so that at room temperature we're both doing this. With my STM I can't tell that because it's too fast, but if I have a defect or if I'm at low temperature, then I can capture one frozen down and the other one frozen up, and that gives rise to that zigzag row that you see. So we've learned something about the dynamics of the surface and barriers associated with it. The lower portion of the image on the right shows what happens when one atom forms a dimer, as it's called, with the other, and the consequence of dimer rows on the terraces. Here's another process that you can have that lets you get up even closer, and that is, suppose that I want to do this at low temperature. Suppose that I know that if I drop the temperature, this thermally activated process will quench out. I want to understand more about that. So let's reduce the temperature, and you can see from these 2 images that the atoms are moving up and down so that the lozengers look uniform. You're down with a partner that's up. My partner over here is down with his partner up. So the repeat length is 1, 2, 3, 4, so it's a 4x2 structure. I'm learning something about the dynamics. I'm learning about things at the atomic scale, which I can then use for subsequent growth studies of silicon. Now there was the Feynman picture of, I'd like to see things at the atomic level, all the way down. And this image lets you see a single atom and identify what it looks like. This is the silicon surface. that has a partial coverage of bromine on it. And it shows you a dimer that has bromine on it and a dimer that doesn't. The dimer that does has two little bright spots. So if you can see in the center of the image, there are rows running upper right to lower left with two bright spots and then an undistinguishable object and two bright spots. Though each of those bright spots is an individual atom. And you can see them, and you can see them routinely, and you can see them for a variety of different materials, and that opens up just an enormous amount of surface science and nanoscience. Seeing atoms, knowing what the processes are. Scanning tunneling microscopy can be done at fixed temperature, but it can be done at elevated temperature. And at elevated temperature, I can watch movies of things changing. So if this works, I should have a movie, I do, a movie of a silicon surface that is slightly reacted with chlorine on it at a temperature of 700 Kelvin. And the time between scans is only 8.5 minutes. And if you focus on a particular part, take your choice, look on a particular object and see how it changes with time. The